Hi, everyone. Thanks for coming. I'm Andrew Zukoski. This is Drew Wolpert. We're here to talk to you about program synthesis for declarative building design. In this talk, we're going to run through our motivation for this. We're going to talk a little bit about buildings and how they get made. We're going to talk about a couple of the technologies that we utilize pretty heavily and that we wanted to share a lot about, SAT solvers and Satisfiability Modulo Theories solvers. We're going to dive into the anatomy of these solvers and how you put them together. And we're going to talk about our experiences augmenting these tools to reason about geometry and shapes. So let's talk about buildings. This is a picture of the Shanghai Tower. It's one of the tallest buildings in the world, second to the Burj Khalifa. It's 126 stories. It's 2 million square feet. It's 4 million square feet of glazing. Oh, no, I have those backwards. Thousands of people go to work in it every day. And it's really pushing forward how the world designs and constructs buildings. It's a really great example of what we're capable of doing. It's a very complicated design. It has this like sort of fascinating double skin where there's this outside layer that sheds a lot of the sunlight and doesn't let it pass into the inhabited spaces inside. So this reduces the electricity utilization of the building in maintaining a sort of appropriate working environment inside. And this is cool. This is the largest building that's ever been LEED Platinum certified. And it is serving as a sort of shining beacon for how well we can design buildings today. And it's good that we can design these sorts of buildings because buildings are really important, right? Construction in the US is 8% of GDP, and I know everyone here like really cares about like economic stuff like that. Let's try CO2, okay? So buildings, their construction and their operation is 39% of CO2 emissions in the United States. Inside of cities, it's even higher. New York City did a study of where their CO2 came from, and they found over 70% came from building construction and building operation. And so this is electricity for the lights, this is electricity for elevators, this is burning natural gas to heat the place. Okay, maybe you don't care about CO2. Even beyond that, most of us spend most of our time inside of buildings, 87%, you might say. And the spaces that we're in have such an important effect on all of our interactions, everything we do every day, that you would expect that architects and software engineers would have gotten together and built the sort of like amazing, fantastic tools that like break down any sort of barriers between thought and construction, simply by conceiving of and demanding, buildings of a certain configuration, of certain performance. We should be able to create these designs and go off and construct them, right? Yes. No. Unfortunately not. Construction and architecture as an industry is an industry that's not received a ton of sort of technological advancement in the last, you can say either in the last few decades or the last few millennia, although I did see a few Procore jackets around. Good job, guys, if you're here. We design buildings largely in the same way that we did 2,000 years ago. We've shifted from drawing on paper to drawing on the computer, but the process is largely the same. It's a very painstaking process. Blueprints are still the de facto way that buildings are designed and reasoned about. Design of a building comes down to figuring out all sorts of details all throughout the building and like minutely pushing around symbols and lines in 2D and 3D drawings. And there are a lot of these details to get right. For a building like this, you have to worry about building code. So this will specify things about occupant safety, health, and wellness. You have concerns about constructability. You can go design something like this, but like if no one can actually put the thing together, then you're out of luck. Owners have their own requirements that they bring to the table. They care about the space and how much of it there is, and they might have sort of special requests about materials. Performance is an emerging concern. So as we said, buildings have a huge environmental impact, and people are waking up and starting to care about this, and states and countries are ramping up energy codes year over year, driving up building performance. And then lastly, designers of buildings bring their own aesthetic criteria that they want to impose on the building to the table. And you have to get all these details right. Oh no, I'm slow, sorry. Yeah, you have to get all these details right, and it's a slow process. So let's talk about parking. Tom Alcorn in the audience knows a thing or two about this. If you're building a parking structure and you want to make sure that there are going to be enough people who can park in it, you have to count the number of parking spots. And the way this is done right now, you might say, oh, it's great. I'll just script something up that we'll lay out each of these spots and we'll have some rules in it about like different egress requirements and spacings and making sure that turning radiuses are large enough. You might think that that's how it's done. That's not how it's done. Right now, the state of the art is that some, probably kind of bummed out junior architect goes and takes the outlines of the parking structure and draws each of the lines for every parking spot. Okay, and then they count the number of parking spots that they just drew, and that's how many parking spots fit in your parking structure. And that's okay, fine, like we do that once, it's great, but you have to do this every time anything about the building design changes. If you push one of the walls, someone has to digitally, I guess, unroll the drawing and go back and revisit each of these parking spots and redraw them and recount them. And it's slow, okay? But it's really important. Cities won't let you construct these buildings unless you have enough parking spots. They don't want you imposing sort of worse traffic problems on downtown. And if you're building a commercial establishment, if people are going to drive there, you want to make sure they actually have places to park. So you have to get this right, and you have to make the best use of the space you have available. Let's talk about safety. If you got a piece of glass that you're going to be near, and you might bump into it and break it, it would be great, because that's probably going to make your day bad enough, if it didn't turn into sort of a set of jagged knives that cut you up and made you bleed out on the floor. That would be awful. And so there are rules out there for where you need to put safety glass that will either resist breakage, or if it breaks, will break in a way that's safe. And these rules are complicated, and they're dependent on the situation that the piece of glass is in. There are different rules for doors, there are different rules for windows, they depend on spacing and whether or not there are barriers. And you got to get all of this right for every piece of glass in the building. You got to get all of this right for every piece of glass in the Shanghai Tower, all 2 million square feet of it. Let's talk about the building exterior. Building exterior is, like many other parts, very important. It has a number of competing things that have to be considered. You have to provide appropriate acoustic isolation so that you can't hear too much of what's going on outside. You have to provide enough insulation that you're not burning through your budget heating the building. You need to keep the water out, and you need to ideally do it in such a way that it's fireproof. So there are these competing concerns, and you have to get all these details right, and you have to do it on a reasonable budget. And these details really matter. This is a picture of the Grenfell fire. It happened in earlier this spring and summer in London, and it's just this incredibly tragic event. And it was caused. There's a lot of reasons that it happened, and so I don't want to trivialize it. But the reason the fire spread so quickly is that someone got the details on the outside of the building wrong. Okay, they used a flammable substance, and they used it with an air gap. So the part of the exterior of the building that worked to shed water had an air gap between it and the insulation underneath. And this meant that if any water did get through, it could run off. The trick is this air gap also acts as a chimney in the case of the fire, which leads the fire to spread much more quickly. And just this incredibly tragic event. So you have to get these details right. But they're not always the most fun thing to reason about. And so we're here asking the question, what if design tools could actively help with this problem? What if, we could take a solver of some sort, embed it in the design tools, and have it figure out the details? Have it satisfy all of these constraints on building design, whether they're code-related, safety-related, fire-related, et cetera. So we think really exciting things. If you're going to start down this path, if you're going to start off and build this thing, you might say, OK, buildings are spatial. I know a thing or two about mechanical design. Can we do this using a geometric constraint solver? And the answer is, well, yeah, let's try. So the geometric constraint solving problem is a problem that's been explored heavily in the mechanical engineering domains. It's used in all of the tools that underlie the design of your iPhone or the design of a car or the bracket that we saw on the last page. And the geometric constraint problem is the problem of given a set of geometric entities, points, lines, curves, planes, whatever, and a set of constraints on them. So things like equality, containment, symmetry around a reflection plane, angle between lines, or tangency between curves, is there an assignment of all of these entities' positions in space such that all of these constraints hold? And this is fairly well-trod field. There are a bunch of implementations out there of this. It's fairly well studied. Most of them work by taking a geometric constraint problem that's composed of entities and constraints on those entities, and decomposing, or transforming it into a constraint graph. So here we've mapped geometric entities to nodes in this graph, and the constraints are mapped to edges between these nodes. Okay, so that's step one. And then I guess that's step 0. We're 0 indexed in all of our procedures. Once we got this graph, the first thing, there's a number of different sort of variations of this, but almost all of these solvers follow a strategy of first decomposing this constraint graph into clusters and creating a solving strategy. So you guys might remember from geometry class in high school how there were, if you had a parallelogram and you knew one of the angles and it was really easy to figure out the opposite angle, or like for certain types of triangles, if you got a little bit of information, there's like very straightforward ways to determine other values in this geometric problem. So when you're doing this decomposition, you leverage rules like that, and you find subproblems that are very straightforward to solve and that you don't have to do any sort of complicated iterative methods to solve. Once you found them, you solve them one at a time and propagate values to neighboring clusters. So you go through, solve a subproblem, take whatever the shared values are, propagate it to another another neighboring cluster, and so on and so forth until you've solved all these problems. Okay, so this is great, right? We're done. We've solved all of the geometric problems, and buildings are largely geometric, and so we have again broken down barriers between thought and construction, and like through sheer force of will are now able to pull whatever things we need from the ground. Not so much. The problem is one of choice. So geometric constraint solvers don't support disjunction very well. It's very exciting how expressive they are. There's all of these different entities that they support, and all the different constraints is very expressive. But it's very difficult to say, hey, I need something to be either the length of the short cinder block or the length of the long cinder block. I don't care which, but it's got to be one of these two. These sorts of things are very difficult to express with existing geometric constraint solving techniques. And this makes it very hard to reason about options or choices in your design. And this is too bad because building design, especially in comparison to mechanical design, is absolutely chock full of choices that you have to make. You choose between different design options or different components. So you might say, oh, this window, it comes in 2 sizes, or these chandeliers, they come in a variety of different sizes or different configurations that would work in different situations. You have different patterns for how you place these things in space. And then you have entirely different strategies that you have to choose from for satisfying different building subsystem requirements. And this is where the geometric constraint solvers break down.
Okay, so a geometric constraint solver isn't going to be enough off the shelf. Let's back up to another of these examples of disjunction that we saw earlier. So one of the sub-bullets in the safety glazing rule is that if the window is large, so greater than 9 square feet, within 3 feet of a walking surface, less than 1.5 feet above the floor, and more than and the top is more than 3 feet tall, so it's placed in such a way that you could fall through it as you're running or walking by, then it needs to be safety glazing. So this doesn't necessarily exactly look like a disjunction to you, but if we rephrase it a little bit, we see that it's either safety glazing or it doesn't meet these other criteria. So this looks a lot like a problem that may be familiar to us as computer scientists, Boolean satisfiability. So does there exist an assignment of variables that satisfies a given propositional formula? This is the first problem proven to be NP complete by Cook in 1971 and then Levin again in 1973 independently. So it's received a fair amount of attention for that reason. It's a search problem. So I'm going to take you back to undergrad CS class for a little while and understand the algorithm that underlies most SAT solvers, even to this day, because understanding this will be important for the extensions that we're going to add to it later to reason about other things besides Booleans. So how do we solve SAT? So this algorithm by Davis, Putnam, Logeman, and Loveland in '79 is basically a backtracking search algorithm with eager application of a couple of ideas. So the first is unit propagation. So if a literal appears alone in a clause, so the clauses are the things between the ands here. So if a literal appears alone, then if it's not true, then the formula is not satisfied. So that literal needs to be true. We can go ahead and assign it to be true and simplify the formula and see what we have left. Second is pure literal assignment. So if there's a literal that always appears in the positive form or always appears in the negative form, then we can go ahead and assign that literal in the form where it appears and simplify the formula, because we know that assigning it that way isn't going to reduce our chances of finding a satisfying assignment. So with these two rules, we can go through and eliminate large, unfruitful sections of our search space and arrive at a solution, if one exists, actually fairly quickly. So let's step through an example. So first, do we see any units that we can go ahead and assign? A, yes. So we can just say A is true, remove that clause. Next, we don't see any more units, but do we see any pure literals that we can assign? Yes. So we remove that clause, great. Do we have any left? Nope, yeah, nothing left. So we have to make a branching choice now. So I'm going to make that choice. Let's say B is true. When we assign B to be true, we can remove a clause, and we can simplify a couple of the other clauses. So now we're left with this simplified formula, and we can go ahead and recurse on that simplified formula. So now let's keep applying our simplification rules. So can we unit propagate? Do we see any units that we can go ahead and assign now? Nope, nothing. How about pure literals? Yep. So C is true. Now we're left with just D's and F's. So now I need to make another choice. Just for fun, I'm going to say that D is false. So when I say D is false, I simplify my formula again, and I see that I have now not F and F. So this is problematic, unsatisfiable. So we turn around and we say, okay, if these other assignments are true, then D cannot be false. So let's backtrack. So now I'm back with D's and F's. So we learned D can't be false. So what happens when D is true? Now we see that we're left with just not F. So that's pretty easy to recurse on. Can we propagate any units? Certainly we can. So now we found a satisfying assignment. We can return that satisfying assignment, and we're all happy. So this algorithm has been around for a long time. It's underlies most solvers. There are a few improvements that can be made to it to make it even more performant. So first is we can backtrack a little bit more intelligently than we did here. So here we just found an unsatisfying assignment and we said, okay, the last decision we made must have been a bad one, so let's backtrack one step. But we can actually analyze the conflict that we have arrived at when we do that and find that, okay, this set of literals can't all be assigned this way at the same time. So we can both backjump to the appropriate decision point and add that new clause that we've learned, which is that this set of conflicting literals can't all be assigned this way together. Add that new clause and continue from that point. So we've actually learned something from the unfruitful branch that we went down. So it's called conflict-driven clause learning. So second, we can make better heuristics for which branches we choose to explore. So people have looked into like when do we want to choose which literals to assign true or false, and how do we branch there. And then when you're starting to reason about large numbers of clauses, it becomes important what types of data structures you use to store your clauses and reason about the unit propagation step. So in practice, we're actually able to handle thousands to millions of clauses this way. Does that mean that we're done? So now we've learned disjunction, and we have geometry, and we have disjunction. Not quite done. So let's go back to our safety glazing example from earlier. So here we'd turned all of these predicates into Booleans. So we had safety glazing, or not, near the floor, large, high, and near walkway. But all the rest of these things besides is it safety glass or not aren't actually Booleans, right? So how do we reason about things that aren't Booleans? So in particular, near floor and high are both inequalities, right? So SAT doesn't know how to reason about these symbols, this like B less than 18 stuff or T greater than 36, but we have other algorithms that are able to efficiently reason about these types of theories. So how can we extend Boolean satisfiability to reason about other useful decidable things? So this is what we call satisfiability modulo theories. So the atoms in our satisfiability formula are no longer just Boolean variables, but they're predicates from other theories like linear arithmetic or arrays or bit vectors. So there are a few different ways that we can do this. One idea is we just convert our formula to a SAT formula. Maybe it's a larger SAT formula, but we now have a SAT formula. This works for some theories. And then we can just feed that into a SAT solver off the shelf and get back a result, translate it back into our theory, and we have an answer. So this works for some theories, and the downside to this is that we end up working pretty hard in the SAT solver to discover things that a solver that understood something about the theory, so a solver, say, that understands the theory of unevaluated functions, would know that if A equals B, then we can also say that f of A equals f of B. But a stat solver has no concept of functions or equality. All it knows about is Boolean variables. So it's not going to be able to do this propagation. It will just have to explore the Boolean search space and come back with an answer if it has one. So we'd like to actually use solvers that understand these theories, because we can. So if we use one of these theories, or use a solver for one of these theories and use a stat solver, each as their own little black box, we can first take our formula as it was and keep all those Boolean variables as atoms, and we feed that formula into the stat solver, and we get back an answer. And now we aren't sure whether it's satisfied in the theory or not, but we can go and feed that into the theory solver and ask the theory solver, is it satisfied in your theory? The theory solver maybe says, yes, it is, and then we're happy. If the theory solver says, no, actually, some of these are in conflict, then it can tell us which ones are in conflict. We can add a new clause, and we can go run our stat solver again. So this is what we call offline, because we are calling out to the stat solver and calling out to the theory solver. So in this architecture, the master solver is just a simple coordinator, and there's a stat solver, which can be any stat solver, exploring Boolean space potentially exhaustively. And then there's a theory solver that just checks all of the stat solver's assignments. So this, again, is nice because we can use a stat solver off the shelf. We can use a theory solver off the shelf. We don't need any particular properties of either of these. It doesn't matter what algorithm either of them uses. But we might like to use the theory solver to actually guide the stat solver. So instead of exploring that Boolean space exhaustively, we want to learn early when we have conflicts in the theory and use that to guide our stat solver so we can stop exploring branches that are going to be unfruitful. So this is what we're going to call an online method. So we have a couple of requirements to be able to do this. So first, the thing that's exploring Boolean space, the stat solver, now needs to be able to accept new clauses. So we're going to use our DPLL algorithm, but now we're accepting new clauses online, as we did in conflict-driven clause learning, from the theory solver. And the theory solver is checking the partial assignments, so partial sets of predicates out of the formula for satisfiability. So let's take a look at how DPLL looks when we've modified it for theories. So we're still doing this backtracking search, and we're eagerly applying the rules that we have for propagating assignments. So one thing to note is that we no longer want to do pure literal assignment here. Since when literals were just true or false, we could safely say that, okay, if it's useful for it to be true or it doesn't harm for it to be true, I might as well assign it. But because a theory solver may find that assigning that literal that way is in conflict with something else that we need to happen, we're no longer going to want to greedily make that assignment. Second is unit propagation. So we can actually learn a lot more with theory solvers in propagation, because it's still true that a predicate that appears alone is going to need to be true for the overall formula to be true, but we also are able to use the theory solvers to deduce more about the truth or falsehood of predicates based on assignments that we've already made. So far I've mostly been talking about using a single theory solver and a stat routine or a single stat solver. But a lot of the problems that we want to reason about aren't just Boolean problems with a single theory added to them. We maybe want to reason about multiple theories, like we have both functions and linear integer arithmetic, or we have arrays and we have integer arithmetic. So let's look at how we can combine multiple decision procedures to have multiple theory solvers working together to help us in the DPLL for the SMT solver. So let's take an example. Here we have a few predicates from both linear integer arithmetic and some unevaluated functions. So we're going to take this algorithm from Nelson and Oppen, which The first step is that we're going to purify the set of predicates into sets of predicates that a single theory solver can reason about. And to do this, we may need to introduce new variables so that the only shared symbols between our two sets of predicates are the variable names and equality. And no theory solver is left trying to reason about symbols that it doesn't understand. Second, once we've done that, we can discover relationships within the theory solvers between variables, and then propagate those relationships to the other theory solvers, and then back up to our sat routine. So back to our example, we see that all of these involve something from the theory of linear integer arithmetic. And the second two also involve symbols from unevaluated functions. So our first step is going to be to purify into predicates of a single theory. So before we do that, let's backtrack for a second and say, what's a theory? So a theory is a set of symbols and operators and associated interpretation rules for them. So like Booleans and or and not, or like plus minus equals greater than less than equal to less than or equal to integers, or equality and unevaluated functions. Those are all theories. Some examples of pure predicates. So A and B is a pure predicate. It's just variables with and. X plus z greater than 2 is a pure predicate. That's just linear arithmetic. F of I equals g of h of j is just unevaluated functions. Some impure predicates. A and b equals 2. We have both Boolean. We have a Boolean operator, but we also have an integer. X plus z of 1 is greater than 2. We have an array, but we also have an integer. F of I equals g of 4. We have a number and we have a function. So now let's purify our example. So first we notice that the first two predicates here are actually already pure. We can just stick those in our theory solver 1 bucket, or T1. The third one is not pure yet. So that one we actually need to split up. So we can do this by introducing a new variable a, and say that a is 1 and f of x does not equal f of a. So then we send the 1 to the left, and we send the unevaluated functions over to the right to T2. We can do that again with our second one. And now we've purified, and we now have a set of predicates that each of these theory solvers can reason about independently. So now what can we learn in each of these theory solvers about the predicates that we have here? So T1 is able to tell us so T1 is, so we're going to reason about what's inside of these, each of these buckets in the theory solver, and then we're going to propagate what we learn over to the other theory solver and eventually up to our parent. So what are the equalities that we're allowed to propagate? So we need to propagate things that are shared symbols between the two theory solvers, because it's not useful for me to propagate something that the theory solver I'm propagating to doesn't understand. So in this case, the only things that we're able to propagate are equality and variables that can be shared. So that's like a equals x equals y, or h doesn't equal g. So first we learn from T1, we can see that either x equals a or x equals b, because we're dealing with integers. We can't tell that one of these particularly is true, but we know that one of them needs to be true. So we can first try propagating the first branch over to T2 and see what we get. So when we do that, we combine x equals a with the predicates that T2 already had, and it tells us, sorry, unsat. So we can backtrack and we say, okay, so x equals a is going to result in a conflict, but what if we choose x equals b instead? So we can send that over. Oh, it unfortunately is not able to say that x equals b either, because f of x does not equal f of a and does not equal f of b. So we've actually learned that this set of 4 predicates cannot all be true together, and we can propagate that back up to our sat routine and use that to continue reasoning about the Boolean logic. Okay, so now we've learned how to use Boolean satisfiability algorithm and pull in theories about other things and reason about them. So we ought to be able to do anything we want to now, right? So back to our safety glazing example. We covered Boolean, safety glazing. We covered these inequalities of integers. We've still got a couple things left, so large and near a walkway. What are these?
Yeah, so we can replace large with a reasoning about the area of the window, and we can replace being quote unquote near a walkway with a distance between whatever the walking surface is and the pane of glass. And so these are examples of geometric predicates. These are the sorts of things that geometric constraint solvers are pretty good at. So what are we going to do? We're going to bring geometry to disjunctions via DPLL theories. And this lets us hopefully reason about disjunctions, different options, and the sort of geometric spatial relationships that underlie a lot of buildings. And that's really going to get us there. We're going to finally be able to, do whatever we want to do with buildings. Let's try it. So this is Rhino. It's a 3D design tool. Maybe some folks are familiar with it. And this over here is a little playground we have for playing with some of these ideas and working on toy problems with some of these program synthesis algorithms. So the first we're going to do, which is just a very simple and common satisfiability modulo theories example, is the send more money problem. Hopefully this is at least somewhat legible. Anyway, the idea is you've got send is a word, more is a word, and if you add them together you get money, which is a word. But wait, it's not. What we do is assign a digit to each of these letters, and we do it in such a way that this little piece of arithmetic holds. And so just to give a feel for how this sort of works, we create logical variables for each of the letters. We make sure that each of the variables is between 0 and 9. We assert that none of them are equal. We construct sort of logical variables that represent the sum of each of these variables. And then at the very end, we assert what we came here to do, which is that if you add these two numbers together, if you add send to more, you get money. So we can come in here, and if we solve this, if we take this up and turn it into a set of SMT clauses and hand it over to the solver, we get back this variable assignments. And as an exercise for the reader, you can go off and check this. Okay, let's look at a really simple geometric thing. Okay, so this is really complicated, right? What we've got here are 3 lines, 1, 2, 3, and a point. And what we want is this point to be on a line, okay? And we don't care which line. We're saying we want, the point can be on the first line, or the point could either be on the second line or the third line. And so similarly, we have these logical variables representing the lines in the point. What we can do is hit the solve button, and this passes this off to DPLL theories. So we've got the Boolean sat solver that's exploring the really complex, again, Boolean space of this simple combination of ORs, and then passes off a particular assignment there and explores different possibilities for how we might assign this point to these different lines. They're actually infinite lines, not line segments. Okay, so we can do that. Let's look at something just a little bit more complicated. So here in this example, we're going to create a trellis. Oop, missing something. We're going to create a trellis, okay? And it's this sort of shape. You might hang things off of it, or maybe just use it to sort of ineffectively block the sun. And so we designed this trellis, and we sort of like the shape, and we like the relationship between these beams, and this is the shape we got, okay? And it's these fixed beams that are linked together. And the beams come, we're placing a beam over here, and what we're saying is, okay, each of these beams is either short, 100 inches long, or it's long, 170 inches long. And what we want is to get this trellis to actually stretch from this column to over here, this pesky detail of actually being, structurally supported. So what we can do is come in here and we're going to add a few assertions. We're going to first assert that the distance between the left column, a sort of structural support point, and the leftmost trellis point is 0.0, right? And we're going to add another constraint for the right one. Okay, and once we've added these two constraints, we're going to be able to first, run it to see whether or not, some assertions are failing. Isn't that interesting? See whether or not we had any typos, which we apparently don't. And now we can take this problem and we can pass it off to the to our solver. Okay, and so what the solver does is it's partitioned this out, and it's taken the Boolean assignments, the choice for each beam, whether it's short or long, and it's taken a sample set of assignments there, and it's propagated into the constraint solver that figures out how to satisfy the requirements that the trellis be supported on both ends, and that each of the beams join at the endpoints. This allows us to explore this design space. So we can pull this in, and now we can start to click through and see different configurations of beam lengths that actually meet the structural points and are legal assignments of different lengths. So we can select one of these, and we can see it, and boom. Oh, we lost the columns again. Where did they go? Now we've got this thing that I swear is supported. Oh, there we go. Hooray! So these are toy problems, and it's been an interesting experiment building these things out and starting to play with them. We have a few anecdotes that we've come up with, or sort of like things that we've learned in going through and actually pulling these things together, and we thought we'd share them for anyone who might be interested in extending SAT and SMT to their own problem space. First is that these are very powerful and very mature technologies. It's really amazing what these technologies can do. And then sort of more excitingly right now, and this is a more recent development, is that the community at this point has a lot of experience in embedding these solvers into new domains. So the type theory community has been doing a lot of really exciting things embedding SAT and SMT solvers. There was a workshop yesterday on reasoning about program correctness using LLVM and Z3 actually. And it's really exciting, so it means there's not only people who can tell you about all the different ways that you put Boolean propositions together, they can tell you about their experience pulling it into and deploying these in new domains. As mature technologies, there exist robust open source implementations for both SAT and SMT solvers. Sort of most prominent in our heads is Z3. It comes from Microsoft. It's under a BSD license. It's this just like, it is not a research project by any stretch of the imagination. It's just like an industrial strength implementation that's been used to solve very important problems. So this is a really ripe set of technologies that's ready for application in new places. It doesn't come without complications. Sort of the biggest one is figuring out the mapping between high-level domain constructs or concepts and the nitty-gritty of individual predicates and clauses. As this presents a few challenges. You can do the mapping, but there's a lot of separation between the problem as you or a user might conceive of it and what actually gets handed to these solvers. This leads to several challenges. First, performance is often opaque. Subtle changes in how a problem is encoded or actual in the specifics of a problem can lead to drastic increases in runtime. You switch from solutions being spat out in fractions of a second to something that takes minutes, hours, or just never solves. Secondly, unsat is hardly a satisfying result. Getting unsat back is a little bit like your compiler helpfully telling you that there's a syntax error somewhere in your program, and if you want to run this program, you should probably figure out where it is and fix it. This isn't new, and there exist tools for expressing and extracting minimal unsatisfiable cores. So from some set of constraints, pull out the hardest part, if you will, and you can say, okay, this is the part. We can solve everything, but we can't solve this part. Unfortunately, that unsatisfiable core is expressed in the nitty-gritty of particular Booleans or particular other theory clauses. And so translating that back out in such a way that you as a debugger or someone else as a user can actually effectively reason about it and understand what it means for their program is a challenge. And just generally explaining how the solvers work to users is confusing. An under-constrained problem will often result in very surprising or non-obvious solutions, and it's challenging for users to sort of work with that. That said, these technologies are amazing. Everyone should pull these out and see what they can do with them. A few resources that we liked when we were getting started. We really want to shout out to Rosette, a project from Mina Torlak, University of Washington, and her collaborators. This is a just amazing system that's embedded Z3 again, actually inside the Racket programming language, and it just completely eliminates any barrier. Well, not any, but it really lowers the barrier to entry to expressing new either solver-aided tools or, in fact, new solver-aided programming languages. So a lot of the sort of mechanics of doing the translation between the sort of programming constructs that we understand and the underlying solver are handled by Rosette, and so it's really easy to dive in and get started. Secondly, Z3 comes from Microsoft. It's amazing. And then for a survey of the solver field, the annual SMT competition, there are new solvers coming out sort of every few years, and the rankings year over year for performance change. So that's a good way to get a survey of the field. That's it. That's us. We'll leave up a few pointers towards anyone who wants to do a little bit further reading, and we'll take questions offline. Thanks, guys.